Hello everyone, welcome to our differential equation class. In this video we are going to use the Laplace transform method to solve initial value problems involving second order linear differential equations. So first we are going to review what is the Laplace transform and how do we use it to solve differential equations. Then we are going to see two examples. The first one is going to be an homogeneous initial value problems, and we are going to solve it using the Laplace transform method. And in the middle of the calculations, we are going to use a method that is called partial fractions. And in the second example, we are also going to solve an initial value problem, but now it's going to be a non-homogeneous initial value problem for the second order differential equation. And in this example, we are going to need to use a different method that is called completing the squares. So that's the plan for today. Let's start with a brief review of the Laplace transform method to solve differential equations. First, the Laplace transform. The Laplace transform of a function, f of t, is to compute the multiplication of the function times an exponential, and then we integrate from 0 to infinity that product in the variable t. The result is going to be a number that depends on this constant s we have here in the exponential, so it's going to be actually a function of s, the result. For some values of s, this integral diverges, and for some values of s, the integral converges. For those values of s where the integral converges is that we define the Laplace transform of the function. For example, the Laplace transform of an exponential is this quotient of 1 over s minus a. And we can do this calculation, so this integral, when s is bigger than a, from a to infinity, in that interval. The right-hand side is defined for s smaller than a, but this integral is not. Therefore, we say that the Laplace transform is defined only for s bigger than a. If you change the function here, you put other functions, well, you get other results. If you put here the sine of at, you get this rational function for the Laplace transform. If you have the cosine, well, then you get this function, and notice that they have the same denominator. The only difference is the numerator. And to use the Laplace transform to solve differential equation, we are going to use the properties of the Laplace transform. For example, the one important property is linearity. Linearity says that the Laplace transform of a linear combination of two functions when a and b are constants is the linear combination of the individual Laplace transforms. We remark that there is no analogous property for the product. If you have a product of two functions and you compute the Laplace transform of that, this is not the products of the Laplace transforms. One property that is almost as important as linearity is the property that the Laplace transform changes derivatives into multiplications. And by that we mean that if you have the derivative of a function and you compute the Laplace transform of that, this is the Laplace transform of the function without the derivative multiplied by s. So this derivative is changed into this multiplication. This equation can be generalized to higher derivatives in a very simple way. For example, the Laplace transform of the second derivative of a function is the Laplace transform of the function multiplied by s squared and some additional terms. So let's prove this property, because it's simple to prove. The only thing we need to do is to use this property here twice, because what we can do is write the Laplace transform of the second derivative as the Laplace transform of the first derivative of the first derivative. And now we use the first equation on the f prime, and we are going to get s Laplace transform of this function here, which is f prime, minus f prime at 0. And now we use that property again, and we have s, and now we are going to have again s Laplace transform of f minus f at 0, and all that minus f prime at 0. And this is how we get the formula s squared Laplace transform of f minus s, the function at 0, minus f prime at 0. There is the analogous property in the other direction. By that we mean that we change derivative into multiplication. Derivative is here on the Laplace transform, and now this derivative is the derivative with respect to s. And this is the same as the Laplace transform of the multiplication of f by t. The generalization of this property to n derivative is very simple. We get here a negative 1 to the power n, and then t to the power n over here. We are not going to use this property in our calculation, so we don't focus too much on the proof, but here it is. The proof is simply for the first equation. Is just recall this this prime is a derivative with respect to s, and then here we have the Laplace transform. So now this derivative can be written inside the integral because we are integrating on t, not on s. And the only part that depends on s here is the exponential, so the derivative goes there. And the derivative with respect to s is going to drop a negative t, which here it is. The negative sign, we put it outside, and then tf is what we are computing the Laplace transform of right now. So very simple to prove. And now we are going to use the Laplace transform and its properties to solve differential equations and initial value problems. But what type of equations? We are going to use it to solve second order because we work with Newton's equations mainly, but it could be higher order. This is not important. So second order could be first order also, but we are going to focus on second order differential equation. But the important part is that the equation has to be linear with constant coefficients, because we want to use linearity, and to use linearity we need these properties, linear with constant coefficients. So if f has this form, if the equation has this form, L of y equal f, then the linear operator L has to be linear with constant coefficients, and the right hand side can be anything, can be piecewise continuous, or more general like Dirac delta, which is the type of right hand side that describes impulsive forces. And what is the idea of the Laplace transform method? Well, the idea to solve differential equation is we compute the Laplace transform of the whole equation. Laplace transform here of the whole equation. And the property that derivatives change into multiplications, this property here and this property, is going to change the differential equation into an algebraic equation. We are going to see that. Algebraic equations are very easy to solve, and the only problem then is to transform back from the Laplace transform of y into y. Because what we are going to get is something of the form, when we solve the algebraic equation, we are going to get Laplace transform of y is some function of s. That is going to be a complicated function, and the idea is, in order to get back to y, is to write this h of s as the Laplace transform of something, because if we do that, then that is our solution. And this is going to be possible because, so once we get this equation, then obviously one solution is y equal h, and this is going to be the only solution with the function we work with, because for continuous functions that they are bounded by exponential, which are the functions we are going to work in our videos, if the Laplace transform of two functions are the same, then the only solution is that the functions are the same. So this is how we are going to find the solutions of differential equations. First of all, we are going to work with linear constant coefficient equations. We are going to transform the differential equation into an algebraic equation. We are going to solve it. We are going to transform back. This is the difficult part. that in a nutshell is the Laplace transform method to solve differential equations. Let's see how the Laplace transform method works, solving a particular example. And the example is going to be to find the solution of this initial value problem. We have here a second order linear differential equation with constant coefficients, homogeneous, and we want to use the Laplace transform method to find the solution of this initial value problem. We will see that somewhere along the calculation we are going to need to use partial fractions. So we will see that in a minute. So what we are actually doing when we use Laplace transforms to solve an equation like this one. What we are actually doing is we are multiplying the whole equation by a function we have chosen to be exponential negative st, both sides of the equation, exponential negative st. Then what we are doing is we are integrating both sides of the equation with respect to the same variable. The variable is t, the independent variable in the equation. And then we are integrating from 0 because that is the initial time in our problem, to infinity because we want to find solutions for all possible values of the variable t. And this is what we are doing, and now we are using integration by parts to move these derivatives to the function we have multiplied the equation by. So we are using integration by parts, and the idea is to, after doing all that, to obtain an equation of the form some coefficients here that they are going to depend on the variable s that we introduced. So coefficients multiplied by this function, which is the Laplace transform of y, plus some other function of s equals 0. Recall this here is a definite integral, so this is equal 0. And what we have here is an algebraic equation for this quantity, the Laplace transform of the solution. Then we do some more work, and we write this algebraic equation in the form everything to the other side. We divide by what we have to divide, and we get the Laplace transform of y equals some function of s. So we have solved the algebraic equation, and now we need to find a function small h so that the Laplace transform of that function is big H. If we do that, then we have solved our problem because the function we are looking for is this small h. So that is essentially the calculation we are doing, but we are not going to use this notation. We are going to use the notation we have introduced in previous videos for the Laplace transform, because if we do it right as we say here, it's going to be too complicated. But if we use a clever notation, everything is much simpler. So for example, let's start where we said we are going to start, with the equation. So the second derivative minus the first derivative minus 2 times y is equal 0. So now we compute the Laplace transform on both sides of the equation, and now we have a notation for that. It's the Laplace transform of y minus y prime minus 2y. And this is equal the Laplace transform of 0, but the Laplace transform of 0 is 0. Now we use linearity to write what we have on the left side as Laplace transform of the second derivative minus Laplace transform of the first derivative minus 2 times the Laplace transform of the original function, all that equals 0. And that is the property of linearity. So let's move everything a little bit more to the right, linearity. So this is the property of linearity. And now we use the other property that derivatives are changed into multiplications, and then we can write this Laplace transform of a second derivative as s squared times the Laplace transform of the function without derivatives minus s. Now we have here the function at 0 minus the derivative at 0. All that is the first term. Then we have minus, and we put here the Laplace transform of the first derivative, which is s, Laplace transform of y minus y at 0. And then we still have the term minus 2 Laplace transform of y, all that equals 0. So now we pull common factor the Laplace transform of y, Laplace transform of y, and Laplace transform of y with whatever they are multiplied by. And then all the rest. So this is going to be equal to s squared minus s minus 2, all multiplied by the Laplace transform of y. And then we are going to have minus s, the function at 0, minus the derivative at 0. And then we have here minus, minus, so it's plus the function at 0. All that has to be equal 0. Now we use the initial conditions. Initial conditions are function is equal to and derivative 3 at the initial time. So this here, this number here is actually 2. This number here is again 2, and this number here is 3. So we end up with the following algebraic equation for the Laplace transform, which is s squared minus s minus 2 Laplace transform of y. Then we have minus 2s minus 3 plus 2 equals 0. Well, here we have an algebraic equation that we said we are going to get. And these algebraic equations are very simple to solve. Notice obviously that this here is actually -1. So we are going to write this -1 on the other side when we solve the equation, and the equation is actually Laplace transform of y is equal, so 2s plus 1 over s squared minus s minus 2. So we have solved the algebraic equation for the Laplace transform of y. Notice, before we continue, that what we have here is not any polynomial, it's actually the characteristic polynomial of the linear operator evaluated at the variable s. But the characteristic polynomial shows up also in the Laplace transform method to solve these equations. Okay, so what do we have here? Well, what we end up with is a Laplace transform of y is actually a function of s that we called before h. Well, now in this example is 2s plus 1 over s squared minus s minus 2. And if the idea now is, let's try to write this right hand side as the Laplace transform of some function h of t. If we do that, then that is our solution. Then the solution we're looking for is that function h of t. But how we do that? Well, the problem is that this function that we have here, what we usually do is we use the Laplace transform table we have constructed to given a function h of s. We look at the table and we get small h of t. But this is not, it's too complicated. This right hand side is not in the Laplace transform table that we have. So we have two possibilities. Either construct a bigger table, a bigger Laplace transform table, or simplify the right hand side. And this is what we are going to do. We are going to simplify this right hand side. And how we are going to do it? Well, with the method we mentioned before, we are going to use partial fractions. But what type of partial fraction we are going to use? Recall this is to simplify the right hand side. So what we're going to do is, let's start with the function h of s. Recall h of s, we said is 2s plus 1 over s squared minus s minus 2. And what we want to do is we want to write it down as addition of simpler rational functions. These are going to be simple fractions. This one here and this one there. That hopefully they are on the Laplace transform table. So how do we do the simplification? Well, to do the simplification, it's important to know the roots on the denominator on your function big H. So let's find the roots of s squared minus s minus 2. That is important. So what are the roots? S squared minus s minus 2 is equal 0. Okay, that means that s plus minus is 1/2. Then we have minus 1, so it's 1 plus minus the square root of negative 1 squared minus 4ac, but c is negative 2. So you see what we get here, we get 1/2 multiplies 1 plus minus the square root of 8 plus 1, 9, square root of 9, which is 3. So we have 1/2, 1 plus minus 3. So that means we have two roots. The root s plus is going to be 4 over 2, so 2. And the root s minus, which is going to be negative 2 over 2, so negative 1. We have two roots. And knowing that these are two different and real roots, allow us to write the function h of s in the form that s plus 1 over s minus 2, because 2 is a root, times s plus 1, because negative 1 is a root. And now, when we have the function written in this way, then it's simple to see by trial and error that this is actually a sum of two simpler fractions. The fractions are s minus 2 in the denominator, s plus 1 on the other denominator, and we have constants here that we need to find. There exist two constants, a and b, so that this is true. Trial and error, this is what the partial fraction method gives us. If we have a rational function like that, it can be written in this form. We only need to find what are the right constants a and b. And how do we find these constants a and b? Well, we do the addition again. So we do the addition. So we have s minus 2 times s plus 1. The addition is going to give us an a multiplied by s plus 1. And over here, b is going to be multiplied by s minus 2. So now we can, because we have the same denominator, what is happening is that the numerators have to be the same. One way to say it is we can simplify the denominators. And then a and b have to be such that, so a and b have to be such that the following equation holds. 2s plus 1 has to be equal a s plus 1 plus b s minus 2, and it has to be true for all s. So we know that a and b exist, so what we can do is we evaluate this equation at different values of s to get what are the values of a and b. One possibility is we evaluate at and the best choices are the roots, negative 1 and 2. So what we are going to do is we are going to evaluate at s equal 2, for example. What happens when we put s equal 2 in this equation that has to be true for all s? Well, then we are going to have 4 plus 1. Here we are going to have a 2 plus 1. And here we are going to have b times 0. That's why we are doing the evaluation at 2, because b disappears from the equation. And we get 5 has to be equal 3a. And that means that a has to be 5/3. So we got a pretty quick. We can do the same to compute b, but now we need to evaluate at the other root at s equal -1. Then we are going to have -2 plus 1 is going to be equal a times 0. That's why a disappears from the equation when we evaluate at the root -1, plus b multiplied by -1, -2. So we end up with -1 is equal minus 3b, and therefore b is 1/3. So these are the two constants such that the equation above is true. So what we have found out is that h of s, that recall was equal to 2s plus 1 over s minus 2 multiplied by s plus 1. Now we know that this has to be equal 5/3. 1 over a is the coefficient of this term, so s minus 2, plus 1/3 s plus 1. So now we have found that, oh, this has to be true. You can verify by adding the right hand side, and you are going to obtain exactly that. So now our Laplace transform of the solution we are looking for is actually, well, it was equal that, but now it's equal that. So let's copy this over. But recall that we know from the Laplace transform table that whenever you have 1 over s minus a, this is the Laplace transform of exponential at. Well, use this equation for a equal 2 and for a equal -1. And what do we get? We get that the Laplace transform of y is 5/3 the Laplace transform of exponential 2t. And then 1/3 the Laplace transform of exponential -t. But the Laplace transform is a linear operation, so this is the Laplace transform of 5/3 exponential 2t plus 1/3 exponential -t. Since these two Laplace transforms are equal, then the functions must to be equal, and then we end up with our solution. Y of t has to be 5/3 exponential 2t plus 1/3 exponential -t. So this is how we use the Laplace transform method to solve an initial value problem for a second order linear differential equation with constant coefficients, and that is homogeneous. Our second and last example in this video is going to be to solve a non-homogeneous second order linear differential equations with constant coefficients but non-homogeneous, and we have some initial conditions. And in this example, somewhere along the calculation, we are going to use what is called the completing the square. We are going to also use partial fractions, but we are going to focus on the completing square part of the calculation. Okay, so how do we solve this problem? Solution. Well, we start where we always start, with the differential equation. y double prime minus 6y prime plus 13y equal exponential 5t, and now we compute the Laplace transform of the whole equation, which means Laplace transform of the left side, Laplace transform of the right side. But we know what is on the right side. This is just 1 over s minus 5. What do we do on the left side? We are doing the calculation a little bit faster than in the previous example. In the left side we have the Laplace transform of the second derivative minus 6 the Laplace transform of the first derivative plus 13 the Laplace transform of y, and recall now this is not 0, this is equal 1 over s minus 5. Now we change derivatives into multiplications, so we end up with here s squared Laplace transform of y minus s, the function at 0, minus the derivative at 0. Then we have plus minus 6. Then the first derivative, Laplace transform of the first derivative is s, Laplace transform of y, minus the function at 0. Then we need to add plus 13, the Laplace transform of y, and all that has to be equal 1 over s minus 5. So let's recall that what are our initial conditions. Y at 0, this number here is actually 1. This number here is 2. And again, this number here is 1. So let's pull common factor like before. Whatever multiplies the Laplace transform of y, which is terms that contain this factor here. So, and that is going to be s squared minus 6s plus 13. Again, this is the characteristic polynomial of the linear operator evaluated at s. And all that is multiplied by the Laplace transform of y. And what do we have? We have from this term we have minus s. Then we have minus 2. And then here we have negative 6 multiplied by negative 1. So this is plus 6. And all that is now not equal 0, is equal 1 over s minus 5. Recall that comes from the right hand side in the equation. So obviously this term here is going to be plus 4. So now we can move it to the other side. So we are going to have s squared minus 6s plus 13 Laplace transform of y, and here we have s minus 4 and then plus 1 over s minus 5. And now we need to divide by the factor both terms. And recall this term comes from the initial conditions, and this term comes from the right hand side of the equation. So this is a nice separation of the solution into two terms, one coming from the initial condition, the rest from the right hand side. And now the Laplace transform of y is s minus 4 divided by the polynomial, the characteristic polynomial, plus 13, and here we have the same, but now we have two factors, s minus 5 multiplied by s squared minus 6s plus 13. So here it is. We have solved the algebraic equation for our Laplace transform, and now we again, let's say it one more time. This term here comes from the initial conditions, and this term here, this part of the solution comes from the right hand side of the equation. And now what we need to do is we need to rewrite this function here that we have is what we have called h of s before. This function is not in the Laplace transform table, so of course let's write it down as the Laplace transform of y is some function h of s, where h of s is obviously this. Copy. Let's put it here. Of course, we are not gonna get it. So this is what h of s is, and of course this is not in the Laplace transform table. So we need to simplify it. And recall, to simplify it, the first step was to see what we have here in the denominator. Here we have s minus 5. This is a factor that we like. But what is that? Now we need to simplify the right hand side, here and here. And recall, to do that, the first step is to find the roots of that denominator, of the polynomial in the denominator. So we need to find the solutions of this equation. And what we have here is two possible solutions. 1/2 minus 6, so positive 6, plus minus the square root of 36 minus 4 times 13. Okay, so one thing we can do now is divide by these two here, and then this 1/2, we can put it inside the square root as a 1/4, which I like it because it's going to simplify this 4, and 36 is going to be divided by 4, so that is going to be a 9. 9 times 4 is 36. So we end up with 3 here, plus minus the square root of 9 minus 13. That is something simple. And then s plus minus, well, we see we are going to have complex roots. 3 plus minus square root of negative 4. So we end up with s plus minus equal 3 plus minus 2i. Which are complex roots. So we have two possibilities here. Do partial fractions. One is do partial fractions with complex roots. With complex roots. What is that? Well, we have shown that our denominator, which is this polynomial, can be written as s minus 3 plus 2i and multiply by s minus 3 minus 2i. Because the roots are complex, but they are roots, so we can work with that. We put that into here and there, and we do the partial fraction decomposition that now is going to have complex number all over the place, or we do what is called so we work with real numbers and we do what is called complete square. So we are going to do the latter one, and what is going to be that completing the square? The idea is we want to write s squared minus 6s plus 13 as s minus some number that we need to find all square plus some other number square. That is what we mean by complete the square. This term here is a complete square plus something else. So we need to find a and b. So that is true. And one way to find it is, well, expand. So expand this s squared minus 2as plus a squared plus b squared, and then make that equal that, this equal that, and solve for a and b. Or another maybe more fancy way is construct it. S squared minus 6s plus 13 is actually equal s squared minus. We multiply by 2 here. If we are multiplying by 2, we need to divide by 2, so we don't change the equation. And there it is. And then times s. And now this number that we have here, which is 3, we add it plus 9, so 3 squared minus 3 squared. You see, here we are adding 0, and here we are multiplying by 1, so nothing has happened in the polynomial. But now we group the first 3 terms, and this is a complete square. This is s minus 3 square, and then we have minus 9 plus 13, which happens to be 4, which is 2 squared. So from here we see that a is 3 and b is 2. So the only maybe strange step is from here to here to here, but here we have used the formula that alpha plus beta squared is nothing more than alpha squared plus 2 alpha beta plus beta squared. So nothing strange going on there, with alpha equal -3 and beta equal alpha equals s. We use this formula with alpha equal s and beta equal -3, and you get that expression here. Okay, so that is our denominator. So now our function h of s looks like this. Let's go to blue again. H of s has, what do we have in the numerator? S minus 4 over s minus 3 squared plus 4, and then here plus, I think it's 1 over, and here we have a product of s minus 5, and then this function we found, s minus 3 squared plus 4. So this is our function h of s. So have we gained anything? Actually, we did, because if you go to the Laplace transform table, we have exponential -80 multiplied by the cosine of bt is actually s minus a over s minus a squared plus b squared, and the Laplace transform of exponential 80 sine of bt, this is b over s minus a squared plus b squared. So clearly we should be using this. You see, this denominator is what we have here for a equal 3 and b equal 2. But the numerators don't match. The numerator here is not, this is, if this should be s minus 3, and we have s minus 4. So what do we do here? So, well, it's a simple trick, simple rewriting. Notice that this function here, s minus 3 squared plus 4, is actually s minus 3 minus 1 over s minus 3. Well, what we can do, let's do it in general. Minus 4 we have here, square plus 4. And what we can do here is we can put the constant we like, and then we add up. Subtract and add, so 0. But you see, now we can split the numerator right here into two fractions, and then we have exactly what we want, s minus 3 over s minus 3 square plus, let's put it 2 square, and here plus, what is this over here? Well, that is a negative 1, isn't it? So minus 1 over s minus 3 square plus 2 square. So the first term is exactly the Laplace transform of exponential 3t cosine of 2t. But the second term is not the Laplace transform of sine, because we have a 1 here instead of a 2, because we have a 2 squared, so we should have a 2 there. But again, this is not a problem because we multiply by 2 and we divide by 2. And now this is minus 1/2 the Laplace transform of exponential 3t sine of 2t. So that's how we use the table to get the first term in the solution written in terms of Laplace transforms. So this term is, we know what to do. What do we do with the second term here? So let's copy that term. Copy. Let's put it here. What do we do here? Well, here we need to do partial fractions again, because there's no other way. So this is going to be some number over s minus 5, and here is not going to be just a number over s minus 3 square plus 4, because the rule for partial fractions is if you have here a polynomial degree 1, then here is a polynomial degree 0. But if you have here, if you have in the denominator a polynomial degree 2, then in the numerator has to be a polynomial degree 1. It's always 1 degree less than the denominator. So here we have bs plus c. That is the right partial fraction decomposition. And the way to do it is the same way we did it in the previous example. We are going to leave it as an exercise. Suppose we have this, we have done the calculation and we have a, b, and c. So what we are going to do is we are going to compute, a, b, and c later. And now we continue the calculation. So suppose we have a and b and c. So now then suppose we have this. Copy, paste. What do we do? Suppose we know what a, b, and c are. Well, then is much simpler now. We need to do a similar tricks as the one we did in the previous problem. So you see here the a is not important, so the a we can put it here, and we can write this as 1 over s. Why? Because this is actually in the Laplace transform table that we work with, but here we have s minus 3, and here there is no s minus 3, so we are going to do what we did before. We are going to subtract 3, but if we subtract 3, we need to add 3, because we need to add 0 at the end. So plus 3. So nothing happened, but all this is multiplied by b. So this is what we are going to do. And then we are going to group the terms like this. So we are going to multiply b by that, b by that. If we do all that, what we have is a, the Laplace transform of exponential phi t. And now here we are going to have two terms. The first term is going to have a b, and then is, well, let's put it all together. So here, b, s minus 3, and then we are going to have plus 3b plus c. All that divided by the same denominator, which is s minus 3 squared plus 4. And now we are going to split this fraction right here. And then we are going to have a Laplace transform of exponential phi t. We didn't do anything here. Here we are going to have b, that is going to multiply s minus 3 over s minus 3 squared plus 4. That is in the Laplace transform table, and then plus, and then we are going to have 3b plus c, all that multiplies 1 over s minus 3 squared plus 4. And recall, here we can multiply by 2 and divide by 2. And this is in the Laplace transform table. And now that we are writing down as in the Laplace transform table, then we put here 2 squared, and we put here 2 squared. And like we did in the previous term, what we end up here is a Laplace transform of exponential phi t plus b, the Laplace transform of exponential 3t cosine of 2t, plus, and now we have this ugly term, 3/2 b plus c over 2, which is just a number, Laplace transform of exponential 3t sine of 2t. And that's it. It looks complicated, but we have solved our problem. Because if we put everything together, the Laplace transform of our solution y of t, recall, is the sum of, and we have, we have that also. So is the sum of these two terms. This first term, we said, is this. Okay, let's copy. Copy. The Laplace transform is this, and then is the plus the other term, but we just found out that the other term is this. Copy, paste. Let's put it here. So that is our solution, which looks a little bit intimidating, but it's not. So now we use linearity, the linearity of the Laplace transform, because these two Laplace transforms and this and this and this, these are just constants. All these are constants. So this is just one big Laplace transform. It's one big Laplace transform of what? The first two terms, exponential 3t cosine of 2t minus 1/2 exponential 3t sine of 2t, and then all the other terms, plus a, recall, is a number that we can compute, exponential phi t, and then plus b is another number that we can compute, exponential 3t cosine of 2t. And then another number that looks ugly but is just a number that we can compute, exponential 3t sine of 2t. So if the Laplace transform are equal, then the functions have to be the same, and that give us the solution. And now notice that we have a lot of common terms. This is common, 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 and then we have two types of terms. We have the terms with the cosine, and then we have the terms with the sine that we can put them together, and then we have the exponential phi t. So our solution, y of t, let's put it here. Our solution, y of t, can be written as, let's start with the term that is alone, exponential phi t multiplied by a. And then we have plus exponential 3t that multiplies the cosine. The cosine has a term 1, which is this term here, and then the b, and nothing else, plus b cosine of 2t. And then we have the term with sines, which is this, minus 1/2. So then we have plus 1/2 that multiplies 3b plus c minus 1 sine of 2t. And that is our solution. The only thing we need to compute to have the full solution is a, b, and c. But this is a partial fraction calculation. So that is our solution. Recall a, b, and c are numbers. So we can exercise is compute a, b, and c. I have these constants computed here below. The calculation is the same calculation as before. You have these two terms. You add them up. Now the denominators cancel out. The denominators are going to cancel. Then you have this big equation for a, b, and c for all s. You rewrite it in some way, and well, at the end you are going to end up with 1/8, 1/8, and negative 1/8. So here is the calculation, but at the end you're going to have a is equal 1/8, b is equal negative 1/8, and c is 1/8. So if you put all these numbers in here, then this is just going to be a number, and another number, and another number, and you have the solution. So this is how we use Laplace transforms to find solutions of second-order linear differential equations with constant coefficients, either homogeneous or non-homogeneous. This is a good place to stop. See you guys in the next video.